So when we first started to look at batteries, we talked about the fact that batteries have three components: the two electrodes, the cathode and the anode, as well as the electrolyte that provides ionic conductivity between the two electrodes. That electrolyte in the middle can have a lot of different chemical identities. One type of electrolyte that's very common in batteries is a so-called solution. And so for the next several lessons, we're going to focus on some of the basics of solutions. We've also seen in the previous lesson that formation of solutions, solvation of ions in solutions, can be a driving force for chemical reactions. Some of the energy that we need to power a battery can come out of solvation effects. So this next series of lessons is going to look at the basics of what a solution is, why solutions form, how we quantify what's present in a solution, and then look at one of the most common types of chemical reactions that we do in solution, which is reactions between acids and bases. What are acids and bases, and how do we quantify those reactions? Once you know those basics of how chemical reactions happen in solution, how we talk about them, how we quantify them, we'll go back to looking at batteries and look at the impact of solutions on performance in batteries. So let's start by defining what a solution is. A solution is quite simply a homogeneous mixture of two or more substances. So for example, if you pop open a Coca-Cola can, you'll find that you've got a solution that's homogeneous. It's a mixture of a lot of different components. Coca-Cola is a homogeneous solution. Solutions can be gaseous. The air that we're breathing right now is a gaseous solution. There's a mixture of a lot of different kinds of gas molecules in the air. Solutions can be solids. The mixture of different elements that we call brass, that's used in creating a lot of ornamental types of objects, is a solid solution. But most commonly when we talk about solutions, we typically mean a liquid solution. So for example, if we take some substance and dissolve it until the liquid is homogeneous, we call that a liquid solution. An example of something that can dissolve to a pretty high amount in water is sugar. One of the large components of Coca-Cola, of course, is sugar dissolved in water. So by definition, a solution is a mixture of two or more substances. That means every solution must contain at least two components. And those two components have distinct chemical names that allow us to track them as chemists. One of those components is called the solvent. The solvent is usually the substance present in the largest amount. So if we take a little bit of sugar and dissolve it in a lot of water, the solvent is the water. What's the name for the sugar at that point? The substance present in a smaller amount is what we call a solute. So the sugar is the solute in that particular circumstance. So let's take a look at another concrete problem. If you dissolve a soup spoon worth of table salt into a glass of water, what's the solvent and what's the solute of the resulting liquid solution? So by definition, the solute is the thing that you don't have very much of, which in this case is the table salt. You've only got about a spoonful of it. On the other hand, the solvent is the thing that you have a lot of. So in this case, the solvent is the glass of water, the water which makes up the majority of the solution. Solutions in which water is the solvent have a special name. They're called aqueous solutions, and they're what we're going to focus on for the rest of these lessons, because they're the most common types of solutions that we encounter in our daily life, and they're actually really important in a lot of industrial applications as well. So I'd like to pause for a moment to look at this series of images. This is a series of images at different stages of dissolving copper sulfate into water. Here on the left-hand side, you see what looks to be about a soup spoon of a blue solid, that's copper sulfate, that's being dropped into water. So you see these clumps of solid that are sort of floating around in the water. Some of them sink to the bottom because they're heavy. And then in the next picture, what you see is a stirring rod. This is sort of the equivalent to a spoon in your kitchen. The stirring rod has been used now to mix that solution so that we don't see particles of copper sulfate anymore. We don't see solid anymore. Instead, in this picture, we have a proper solution. It's homogeneous looking. All the solid has been dissolved. And what we get is a light blue solution, which is copper sulfate, which has been solvated or dissolved by the water molecules. Here in this third picture, we have a more concentrated solution of copper sulfate in water. So the difference between this middle picture and this right picture is that there's more solute in the solution. As we dissolve more copper sulfate, the solution gets darker because the copper sulfate is interacting with the light and causing us to have that color. It's not the water that's making this solution blue, it's the copper sulfate. It's the copper ions in solution. I wanted to show you this series of pictures because it represents, in a sense, stages of solution formation, which is what we're going to talk about for the last part of this lesson. Solution formation can be thought of as occurring in 3 distinct steps, a bit like what you see in the images above. In the first step, a solid solute has to separate into particles. So in this picture of the copper sulfate in water, big clumps of solid have to become smaller clumps of solid. And ultimately, we have to be breaking down our solid into smaller bits. And you can still see in this second image, there's some smaller bits of solid that are accumulating in the bottom of the beaker, which by the third image are completely gone. So the first step to solution formation is this breaking apart of solute structures into smaller either molecules or formula units or parts of an ionic structure. This process requires energy because it's basically breaking interactions that already exist between the solute molecules or solute ions. In the second stage of solution formation, solute particles need to move away from each other to make space for solvent. That's loosely what we're seeing in the middle image in this particular figure of the copper sulfate. Again, that's an endothermic step because it's breaking those solute-solute interactions until they're even smaller. In the final step of solution formation is really what energetically drives solution formation, and that's mixing of the solute and solvent particles. And that's what we see in this other image here on the left. Let's take a look for a moment at this image here on the left. This is a crystal of table salt, crystal of sodium chloride, which on the left side is shown in its crystalline form. And then we are to imagine that it's being dissolved by water molecules. Now, before we start to think about how it's dissolved, it's worth remembering that water has a very strong dipole, so that water carries a very high negative charge on the oxygen end of the molecule and a large partial positive charge on the hydrogen ends of the molecule. So when a sodium chloride salt starts to break apart into ions in a water glass, what happens from the perspective of intermolecular forces? Well, salt is comprised of sodium cations and chloride anions. The sodium cations carry a positive charge. The chloride anions carry a negative charge. Those ions become hydrated in aqueous solution. What does that mean? That's what this image here on the right-hand side is. On the right-hand side, we see a picture of a sodium cation surrounded by what we call hydration sphere of water molecules. In essence, this is a collection of water molecules around the sodium cation that are all oriented such that the negative side of the water molecule, that is the oxygen, is pointing towards the sodium cation. So you can see in all cases, the oxygen atom is oriented towards the sodium cation. Why should that happen? The oxygen atom is carrying a partial negative charge. The sodium cation is carrying a full positive charge. So this is an example of an ion dipole interaction. This is a pretty typical type of interaction that you see when an ionic solid, like table salt, is dissolved into a polar solvent, like water. You can see when you look at the bottom part of the figure that the same type of interaction happens between the chloride anions and the water molecules. But instead of the oxygen atoms orienting themselves towards the chloride, in this case, the hydrogen atoms orient themselves towards the chloride because the hydrogens carry a partial positive charge and the chloride carries a full negative charge. So again, an ion dipole interaction forms between each water molecule that's attracted to the halogen anion, just like water was attracted to the sodium cation. And these ion dipole interactions release energy, so that the process of solvating these ions releases energy. This is an exothermic process. Now, remember that this process is also organizing the water molecules into a hydration shell around the anion. That's also decreasing the entropy. And you remember that in order to predict whether a reaction is spontaneous or not, we need to consider both enthalpic or energetic contributions and entropic or statistical or randomness contributions. So in this particular case, dissolving sodium chloride in water releases a significant amount of energy because of the formation of these ion dipole interactions that is sufficient to overcome the loss of entropy of the water organizing itself around the ions, so that dissolving sodium chloride in water is a spontaneous process. And in fact, sodium chloride is highly soluble in water because of these strong ion dipole interactions, this strong energetic driving force for forming individually solubilized ions. And we see this with a lot of ionic salts in water. Because of the high polarity of water and the high charge on the ions, ionic salts tend to be very, very soluble in aqueous solutions. We'll come back to the idea of quantifying how much of something's in an aqueous solution in the next lesson.